Hey everyone, and welcome to another deep dive. Today we're tackling something that's pretty fundamental to, well, everything.
We are.
Yep, gravity.
Oh, okay, cool. Yeah, gravity is definitely one of those things we kind of take for granted.
Totally. Like it's just there doing its thing, keeping us grounded. But
Mm.
when you actually stop and think about it,
Mhm.
it's pretty mind-blowing.
For sure. I mean, it's the reason why planets orbit stars, why galaxies hold together, even why black holes exist.
Exactly. It shapes the entire universe. And, you'd think with something so universal, we'd have it all figured out by now.
Well, we've come a long way since, the ancient Greeks who thought everything revolved around the Earth.
Right. Good old Ptolemy and his Earth-centric model. But then along came Copernicus, who kind of flipped the script.
He did. Copernicus was like, hold on, what if the sun is actually at the center and everything else, including Earth, revolves around it?
Talk about a paradigm shift. But even Copernicus didn't have all the pieces of the puzzle, right?
Right. That's where Tycho Brahe comes in. He was this meticulous astronomer who spent years making incredibly precise observations of the planets.
I've heard he had this whole observatory island set up. Talk about dedication. But what did he do with all that data?
That's where Johannes Kepler enters the picture. He was Brahe's assistant, and he inherited all those amazing observations.
And Kepler was the one who figured out the laws of planetary motion.
Yeah. 3 laws that basically describe how planets move around the sun.
Okay, so let's start with the basics. Newton's law of gravitation. Like, what's the big idea?
Well, Newton's insight was that every object in the universe attracts every other object with a force. And the strength of that force depends on 2 things.
Hit me with him.
First, the masses of the objects. The more massive the objects, the stronger the gravitational force between them.
So like me and the Earth, we have a pretty strong attraction going on. Makes sense since the Earth is a bit bigger than me.
Exactly. And the second factor is the distance between the objects. The farther apart they are, the weaker the gravitational force.
So it's a cosmic tug of war where mass and distance are constantly in play.
Okay, that makes sense, but I gotta admit, I've always struggled with that whole inverse square law thing.
Yeah, it can be a bit tricky to wrap your head around, but basically, it means that if you double the distance between 2 objects, the gravitational force between them becomes 4 times weaker.
Oh, okay, so it's not a linear relationship. The force drops off pretty quickly as the distance increases.
Exactly, and that's why, even though every object in the universe is pulling on every other object, the gravity we feel most strongly is from the Earth because, well, it's right under our feet.
Makes sense. But, I've heard there's a catch with Newton's law. It works perfectly if we're dealing with point masses or perfectly spherical objects, but the real universe is a lot messier than that.
Right. The real world has lumpy potatoes and irregularly shaped asteroids. Objects with all sorts of shapes and densities.
Yeah, so how do we even calculate gravity when things aren't so neat and tidy? Well, in those cases, we have to get a bit more sophisticated. Instead of treating the object as a single point, we break it down into tiny pieces, each with its own mass and position.
Oh, so it's like a cosmic jigsaw puzzle where you have to add up the gravitational pull of all the individual pieces.
Exactly. And while the math gets a bit more complicated, the basic principle remains the same. Mass attracts mass.
Okay, that makes sense. Now, I got to ask about this mysterious G thing, the gravitational constant. It shows up in Newton's equation, and it's such a tiny number.
Tiny but mighty. G represents the strength of the gravitational force. And you're right, it's incredibly small, about 6.67 by 10 to the power of a method 11.
Wow, that's a lot of zeros after the decimal point. What makes it so special?
Well, G is what we call a universal constant. It means it has the same value everywhere in the universe.
Whoa, that's mind-boggling. It's like a cosmic rule that applies everywhere, no matter where you are in the vastness of space.
Exactly. And even though G is tiny, its effect is profound. It's the glue that holds galaxies together, the force behind the orbits of planets and stars.
So it's like a tiny seed that gives rise to this massive cosmic tree.
A beautiful analogy. But I'm curious, how did we even figure out the value of this incredibly small G? It seems like trying to measure something so subtle would be almost impossible.
Right. Like what kind of cosmic ruler did they use?
Well, it took a brilliant scientist named Henry Cavendish to crack this puzzle back in the 18th century.
Okay, I'm all ears. How did he manage to measure something so tiny?
Cavendish used a really ingenious experiment involving a torsion balance. Imagine a delicate rod suspended by a thin wire with 2 small lead spheres attached to its ends.
Okay, I'm picturing it.
Yeah.
Sort of like a tiny cosmic mobile.
Exactly. And he placed 2 larger lead spheres near the smaller ones, and because of gravity, Those tiny spheres were ever so slightly attracted to the larger ones.
Ah, so he basically created a mini gravitational system in his lab.
Exactly. And by measuring how much that rod twisted because of that tiny gravitational attraction, Cavendish was able to calculate the value of G.
Wow, that's incredible. Such a simple experiment, yet it unlocked one of the fundamental constants of the universe.
It's a testament to the power of human curiosity and ingenuity. And speaking of G, I think it's worth pondering this. What if G had a different value? How would our universe be different?
Whoa. Yeah, mind blown. I mean, we've talked about how even tiny tweaks to the laws of physics can have huge consequences.
Absolutely. If G were larger, gravity would be a much stronger force. Stars would burn hotter and faster, their lives would be shorter, and planets might be crushed under their own weight.
Okay, so a stronger G means a more intense, shorter-lived universe. Not exactly a recipe for a stable cosmos.
Exactly. And if G were smaller, gravity would be weaker, stars might not form at all, and planets would have a harder time holding onto their atmospheres.
So we're kind of in this Goldilocks zone where
Yeah.
G is just right for a universe like ours to exist. That's pretty incredible when you think about it.
It really is, and it makes you wonder, why is G the value it is? Is it just a random coincidence, or is there some deeper reason?
That's a question that has kept physicists up at night for a long time. And it's one we might explore further down the road. But for now, let's bring things back down to Earth, literally.
Sounds good. Time to get grounded.
Exactly. Let's talk about something we experience every day, the acceleration due to gravity. Or G, the thing that keeps us from floating off into space.
Right. G is essentially what we feel as weight. It's the rate at which objects accelerate towards the Earth because of gravity, and on Earth, it's roughly 9.8 meters per second squared.
Okay, that number always makes me think of physics class.
Mm-hmm.
But what does it actually mean?
Well, it means that every second an object falls, its speed increases by 9.8 meters per second.
So if I were to, hypothetically speaking, of course, jump off a building, I'm not recommending this.
Yeah.
I'd be getting faster and faster as I fell. Not a pleasant thought.
Not at all. But luckily, we have things like the ground to stop us. But the point is, G is what determines how strongly we're pulled towards the Earth.
And it's also why a feather and a bowling ball, despite their very different masses, would fall at the same rate in a vacuum.
Right.
You got it. In the absence of air resistance, everything accelerates at the same rate due to gravity.
Cool. So G is constant, right? Like everywhere on Earth, it's always 9.8 meters per second squared.
Well, not exactly. It actually varies slightly depending on a few factors.
Oh, like what? I thought G was supposed to be this universal constant thing.
It is in the sense that the gravitational constant G is the same everywhere, but the actual acceleration due to gravity G can change slightly depending on where you are on Earth.
Interesting. So what can cause those variations?
Well, for one, altitude. The farther you are from the Earth's center, the weaker the gravitational pull, and therefore the slightly lower the G value.
So if I'm on top of Mount Everest, gravity's pull on me would be slightly weaker than if I'm at sea level.
Exactly.
Yeah.
And the difference is measurable, though you probably wouldn't feel it.
So technically, I'd weigh slightly less on Mount Everest. I might need to add that to my bucket list. Ha! Well, the difference is tiny, but it highlights the fact that G isn't perfectly uniform across the Earth.
Okay, so altitude is one factor. What else can affect G?
The Earth's rotation also plays a role. Because the Earth spins, objects at the equator are actually moving faster than objects at the poles.
Ah, right. I remember that from my geography days.
Oh.
The Earth is like a spinning top, and points further out from the axis spin faster.
Exactly. And that extra speed at the equator creates a slight outward force, a centrifugal force, that counteracts gravity ever so slightly.
So objects at the equator experience a slightly weaker G value compared to the poles because of that outward force.
That's right. It's another subtle variation, but it shows how even something as fundamental as gravity can be influenced by other factors.
Wow, gravity is way more complex than I initially thought. I'm starting to see it everywhere now, like in those spinning carnival rides that push you outwards.
Exactly. Centrifugal force is at play there too, mimicking the effects of a weaker gravitational field.
That makes me think of astronauts in space, floating around in that weightless environment. Is that because there's no gravity in space?
That's a common misconception. Astronauts experience weightlessness not because there's no gravity, but because they're in a constant state of free fall.
Free fall, like skydiving.
Exactly. Imagine jumping out of a plane. For a brief moment before the parachute opens, you feel weightless because you're falling at the same rate as everything around you, including the air.
Okay, so it's like that feeling you get at the top of a roller coaster when your stomach lurches.
Exactly. Now, astronauts in orbit around the Earth are constantly falling towards the planet, but their forward motion is so fast that they keep missing it.
It's like they're perpetually falling around the Earth, never quite hitting the ground.
Precisely. And because they're falling at the same rate as their spacecraft, they experience weightlessness. It's like a continuous, controlled free fall.
Wow, that's a pretty amazing way to think about it. And it makes me wonder, if weightlessness is all about free fall, could we create artificial gravity on spacecraft, for long-duration missions to other planets?
That's a question scientists and engineers are actively exploring. One idea is to use centrifugal force to mimic the effects of gravity.
Oh, like those spinning space stations we see in sci-fi movies.
Exactly. By spinning a spacecraft, you could create an outward force that pushes objects against the hull, simulating the feeling of gravity.
It's like turning a spaceship into a giant rotating carnival ride.
In a way, yes. And it's not just science fiction. There are serious proposals to design and build rotating habitats for future space missions.
That would be incredible. Imagine waking up in a space station and actually feeling the pull of gravity, even if it's artificial.
It would certainly make life in space a lot more comfortable. And it would help mitigate some of the health issues astronauts face due to prolonged exposure to weightlessness.
This is getting me really excited about the future of space exploration. But speaking of breaking free from gravity's pull, let's talk about escape velocity. How fast would you have to throw a ball to make it leave Earth forever?
Yes. Escape velocity, the speed an object needs to reach to overcome a planet's gravitational pull. For Earth, it's about 11.2 kilometers per second, or over 40,000 kilometers per hour.
Whoa, that's incredibly fast, like way faster than any car or plane I've ever seen.
For sure. It takes a lot of energy to reach that speed. And it's not just about going up. The object needs to be moving sideways fast enough so that its path curves away from Earth instead of falling back down.
So it's like throwing a ball so hard that it curves around the planet and keeps going.
Exactly. And once an object reaches escape velocity, it's essentially free from Earth's gravitational grasp and can continue traveling out into space.
It's like a cosmic slingshot, launching an object out of Earth's reach and into the vastness of space. But is escape velocity the same for all objects, regardless of their mass? Like, would a tiny pebble need to be launched at the same speed as a giant rocket?
That's a great question, and surprisingly, the answer is yes. Escape velocity depends on the mass and radius of the planet, not the mass of the object being launched.
Whoa, that's counterintuitive. But I trust the physics, and I bet the escape velocity is different for other celestial bodies, right?
Yeah.
Like, is it easier or harder to escape from the moon compared to Earth?
Absolutely. The moon's escape velocity is only about 2.4 kilometers per second, much lower than Earth's because the moon is less massive and has a weaker gravitational pull.
That makes sense. It's no wonder we were able to land astronauts on the moon and bring them back. It seems like we're starting to get a handle on how gravity plays out across our solar system. Now let's dive into something that's always captured my imagination. The elegant motion of planets around the sun. I'm talking about Kepler's laws, right?
You got it. Johannes Kepler, building on the work of Tycho Brahe, figured out 3 laws that describe planetary motion with incredible accuracy.
I'm all ears. So hit me with Kepler's first law. What's the scoop?
Kepler's first law, also known as the law of orbits, states that planets don't move in perfect circles around the sun.
Wait, what? I always pictured the solar system as this neat and tidy collection of circular orbits.
Yeah, that's a common misconception. In reality, planets move in ellipses, which are kind of like stretched out circles.
Oh, okay, so they're more like oval-shaped paths. So a planet's distance from the sun isn't constant. It gets closer at some points and farther away at others.
Exactly. And the sun isn't located at the center of the ellipse, but at one of the 2 foci.
Okay, I'm starting to picture this cosmic oval racetrack. So the planets are zipping around the sun, sometimes getting closer, sometimes swinging farther away. And that brings us to Kepler's second law, right? The law of areas.
You got it. This law describes how a planet's speed changes as it orbits the sun.
Okay, I'm intrigued. So does a planet speed up when it's closer to the sun and slow down when it's farther away? That would make sense, right? More gravity, more speed?
Exactly. Imagine drawing a line connecting a planet to the sun. As the planet moves along its elliptical path, this line sweeps out equal areas in equal times.
Okay, so equal areas in equal times. I'm trying to visualize that.
Think of it this way. When the planet is closer to the sun, the line connecting it to the sun is shorter, so it has to move faster to sweep out the same area as when it's farther away and the line is longer.
Ah, okay, I'm starting to get it. It's like a cosmic dance where the planet speeds up when it's closer to its partner, the sun, and slows down when it's farther away. Now, what about Kepler's third law? What does that tell us about planetary motion?
Kepler's third law, also known as the law of periods, connects a planet's orbital period, the time it takes to complete one orbit around the sun, to the size of its orbit.
So does this mean planets farther out from the sun take longer to orbit?
Exactly. Kepler's third law states that the square of a planet's orbital period is proportional to the cube of the semi-major axis of its orbit, which is basically the average distance between the planet and the sun.
Okay, so a planet twice as far from the sun would take much longer to orbit, not just twice as long. It's a precise mathematical relationship that governs the entire solar system.
Exactly. And it's one of the reasons why we can predict the positions of planets with incredible accuracy, even centuries into the future.
It's amazing how Kepler was able to figure all of this out just by analyzing Brahe's observations. It's a testament to the power of careful observation and mathematical reasoning.
For sure. And these laws aren't just about planets either. They apply to anything orbiting under the influence of gravity, from moons around planets to stars around the center of a galaxy.
So it's like a universal language of motion, a cosmic code written in the stars themselves. But speaking of things orbiting Earth, let's talk about those marvels of modern technology satellites. They're basically mini planets, right? But how do we actually get them up there and keep them in orbit?
That's where the magic of rocket science comes in. Launching a satellite is all about overcoming Earth's gravity and achieving a specific speed and direction, what we call orbital velocity.
Okay, so it's more than just shooting a rocket straight up.
Definitely. If a rocket just goes straight up, it'll eventually fall back down to Earth. To stay in orbit, a satellite needs to have enough horizontal velocity to constantly miss the Earth as it falls.
So it's like finding that sweet spot between going up and going sideways fast enough to stay in a constant state of free fall around the planet.
Exactly. It's like throwing a ball so hard that it curves around the Earth and never quite hits the ground.
Wow, that's pretty mind-blowing.
Yeah.
But how do we ensure that a satellite stays in a stable orbit? I imagine there are all sorts of forces trying to pull it off course.
That's true. Things like atmospheric drag, the gravity of the moon and sun, even solar radiation pressure can affect a satellite's orbit over time.
So it's a constant battle against these cosmic forces.
You could say that, but to counteract those forces and keep a satellite in its desired orbit, we use onboard thrusters.
Ah, like little rocket engines that can nudge the satellite back on course.
Precisely. These thrusters make tiny adjustments to the satellite's velocity and orientation, allowing it to maintain its orbit for years or even decades.
It's amazing how we can harness our understanding of gravity to keep these machines soaring through space. And it makes me think about all the different types of orbits satellites can have. Like we've talked about circular and elliptical orbits. Are there others?
Oh, definitely. There's a whole variety of orbits depending on the satellite's mission.
Like what?
Well, some satellites, like those used for communication, are placed in geostationary orbits.
Geostationary, what's special about those?
These satellites orbit at a specific altitude and speed that keeps them above the same point on Earth's surface.
So they're basically hovering over the same spot.
Yeah.
That's pretty cool.
Yeah, it's ideal for things like satellite TV or weather monitoring because the satellite always has a fixed view of the same region.
That makes sense. And what about those satellites that study the Earth's polar regions? They must have a different kind of orbit.
You're right. Those satellites use polar orbits. As the name suggests, they pass over the Earth's poles on each orbit.
So they're constantly sweeping over different parts of the planet.
Exactly. Polar orbits are great for collecting data on things like ice cover, ocean currents, and atmospheric conditions over the entire globe.
It's amazing how we can tailor a satellite's orbit to its specific mission. It's like choosing the perfect dance move for each cosmic performance. But I have a feeling we've only scratched the surface of the world of satellites.
We have. There's so much more to explore, but for now, I think we need to take a break from our orbital adventures.
Agreed. We've covered a lot of ground today, from Newton's laws to escape velocity to the intricate dance of satellites.
And there's still so much more to unravel.
That's the beauty of a deep dive. There's always more to discover.
Welcome back to our deep dive into gravity. Last time, we left off with this whole idea of satellites and orbits, remember?
Oh yeah, definitely. It's amazing how we can use our understanding of gravity to send these machines soaring through space.
It really is. And speaking of cosmic dances, There's another type of gravitational partnership I'd love to explore, binary stars.
Binary stars, I've heard of those. They're like two stars luck in a cosmic tango orbiting around each other.
Exactly. It's like a celestial ballet, with two stars swirling through space, bound by their mutual gravitational attraction.
Okay, I'm picturing this cosmic dance floor, but how does it actually work? What are the rules that govern their motion?
Well, just like planets orbiting the sun, binary stars orbit around a common center of mass.
A center of mass.
Yeah, think of it like a balancing point between the two stars.
So it's like a seesaw, where the position of the fulcrum depends on the weight of each person sitting on it.
Precisely. The more massive the star, the closer the center of mass will be to it.
So in a binary system with two stars of equal mass, the center of mass would be right in the middle.
You got it. But if one star is much more massive than the other, the center of mass will be closer to the heavier star.
So it's like a cosmic tug-of-war, where the more massive star has a stronger pull on the center of mass.
Exactly. And as the stars orbit around this common center of mass, their distance from each other changes, creating a beautiful and intricate dance.
Okay, that makes sense. But how do we even know that binary stars exist? I mean, they're so far away, wouldn't they just look like a single point of light?
That's a great question. And you're right, it can be tricky to distinguish binary stars from single stars, especially if they're very close together.
So how do astronomers figure it out?
Well, there are a few different methods. Sometimes, if the stars are far enough apart, we can actually see them as separate points of light through telescopes.
So we can actually see them orbiting each other.
Yep. In those cases, it's like watching a slow-motion cosmic waltz unfold over time.
That's incredible. But what about binary systems where the stars are too close together to be resolved visually?
For those systems, astronomers have to get a bit more creative. One way is to look for changes in the star's light as they orbit each other.
Changes in their light. How does that work?
Well, imagine two stars orbiting each other. As one star moves towards us, its light waves get compressed, causing a slight blue shift in its spectrum.
A blue shift. So its light appears slightly bluer than it normally would.
Exactly. And as the star moves away from us, its light waves get stretched out, causing a red shift.
So it looks a bit redder.
Precisely. By carefully analyzing the light from a star, astronomers can detect these subtle shifts in color, revealing the presence of an unseen companion.
That's amazing. It's like deciphering a secret code hidden in starlight. And this technique works even if the stars are too close together to be seen individually.
Exactly. It's one of the most powerful tools astronomers have for detecting and studying binary stars.
This is blowing my mind. So we can actually see the dance of binary stars even when they're hidden from our direct view.
Yep. And it's not just about watching their dance moves. By studying binary star systems, we can learn a lot about the fundamental properties of stars, like their masses, sizes, and temperatures.
So it's like these cosmic couples are giving us clues about the lives of stars in general. That's pretty cool. But I'm curious, how do these systems form in the first place? Do stars just kind of bump into each other and get locked in this gravitational dance?
It's unlikely that stars would just randomly collide and form a binary system. The vast distances between stars make such encounters extremely rare.
So what's the more likely scenario?
Well, the prevailing theory is that binary stars form together from the same cloud of gas and dust.
So they're like cosmic siblings born from the same stellar nursery.
Exactly. As a giant cloud of gas and dust collapses under its own gravity, it can fragment into smaller clumps, each of which can eventually condense and ignite into a star.
So if two of these clumps form close enough to each other, their mutual gravity can bind them together, creating a binary star system. That makes sense. It's like a cosmic family affair. But what happens when the stars in a binary system reach the end of their lives? Does their dance continue, or does it end in a dramatic finale?
That's where things can get really interesting. The fate of a binary star system depends on the masses of the stars and how close they are to each other.
Okay, so different destinies depending on their cosmic circumstances. Tell me more.
In some cases, if the stars are far enough apart, they can evolve relatively peacefully. They'll eventually run out of fuel, puff up into red giants, and then shrink down into white dwarfs, fading away like cosmic embers.
So their dance continues, even as they age and transform.
Exactly. But if the stars are closer together, things can get a bit more dramatic.
Oh, like what kind of drama?
Well, imagine two stars orbiting each other, one of them a red giant that's swollen up to many times its original size.
Okay, I'm picturing this giant puffed up star looming over its companion.
Right. Now, if those stars are close enough, the red giant's outer layers can actually spill over onto its companion. It's like a cosmic transfusion.
Whoa. So one star is basically stealing material from the other.
Exactly, and that transfer of mass can have some pretty dramatic consequences.
Like what?
Well, for one, it can speed up the companion star's rotation, making it spin incredibly fast.
So it's like a cosmic figure skater pulling in their arms to spin faster.
A perfect analogy. And this rapid spinning can create powerful magnetic fields and intense stellar winds, spewing out streams of particles into space.
Wow, that sounds intense. So binary stars can be quite the dynamic duo. But what happens to the red giant after it loses all that material?
Eventually, the red giant will shed its outer layers completely, leaving behind a dense, hot core called a white dwarf.
So it's like a cosmic butterfly emerging from a stellar cocoon.
I like that. And in some cases, if the white dwarf is close enough to its companion, it can start pulling material away from it, creating what's known as an accretion disk.
An accretion disk, what's that?
It's a swirling disk of gas and dust that spirals inward towards the white dwarf like water going down a drain.
Okay, picturing this cosmic whirlpool around the white dwarf.
Exactly. And as this material falls onto the white dwarf, it can heat up and release bursts of energy, creating spectacular astronomical phenomena like novae and supernovae.
Oh, supernovae. Those are like the grand finales of the cosmos.
Yeah,
Exploding stars that briefly outshine entire galaxies.
you got it. And it's amazing to think that these incredible events can be triggered by the interaction of stars in a binary system.
Binary stars are way more complex and dramatic than I ever imagined. It's like they're the ultimate cosmic power couples, shaping the evolution of galaxies and seeding the universe with heavy elements.
Absolutely. They're a constant source of fascination and wonder, reminding us that the universe is a dynamic and ever-evolving place.
Okay, I'm officially hooked on binary stars. But I know there's more to gravity than just orbits and stellar evolution. We touched on gravitational potential earlier. Can we dive into that a bit more?
Sure, it's a concept that can be a bit tricky to wrap your head around, but it's fundamental to understanding how gravity works. Think of it as a way to describe the influence of gravity at a particular point in space.
So like a map of gravity's strength.
In a way, yes. The higher the gravitational potential at a point, the stronger the gravitational pull an object would feel at that location.
Okay, that makes sense. So objects naturally want to move from regions of higher gravitational potential to regions of lower gravitational potential, like rolling down a hill.
Exactly. Just like a ball rolling down a hill, objects tend to move towards regions where they can minimize their gravitational potential energy.
So it's like gravity is constantly trying to pull things downhill on this cosmic energy landscape.
A great way to put it. And this concept of gravitational potential applies on all scales, from the motion of planets around stars to the formation of galaxies, and even the expansion of the universe itself.
Wow, so it's really a fundamental concept that underlies everything we've been talking about.
Exactly. And it's one that we'll continue to explore as we delve deeper into the mysteries of gravity.
This is getting me really excited about what's next. But before we jump ahead, I think we need to take a break and let our listeners digest all this amazing information about binary stars and gravitational potential.
Agreed. We've covered a lot of ground today, but there's still much more to explore.
Welcome back, everyone. It's amazing to think about how much ground we've covered in our deep dive into gravity.
I know, right? From Newton's laws to binary stars to gravitational potential, it's been quite a journey.
It has. But there's one more fascinating aspect of gravity I'd love to explore, one that's kind of hidden from our everyday experience.
Oh, what's that?
Gravitational pressure. The crushing force generated by the weight of a planet's or a star's own layers.
Ah, yes. Gravitational pressure. It's mind-boggling to think about the forces at play deep within these celestial objects.
I know. Like, imagine the Earth. All those layers of rock and metal piled on top of each other, creating unimaginable pressure at the core.
It's like a cosmic vice squeezing the planet from all sides. And that pressure is what drives so many of the dynamic processes we see, both on Earth and in stars.
So it's not just about objects falling to the ground or orbiting each other. Gravity is also shaping the very heart of these celestial bodies, right?
Exactly. Gravitational pressure plays a key role in things like plate tectonics, volcanic activity, and even the generation of Earth's magnetic field.
Wow, so it's like a hidden sculptor, shaping the planet from the inside out. But I gotta ask, how do we even begin to calculate this pressure? It seems like a pretty daunting task.
It definitely involves some serious math. But essentially, we have to consider the distribution of mass within the object and how the gravitational force changes at different depths.
So the deeper you go, the stronger the gravitational pull, and therefore the higher the pressure. It's like descending into a cosmic pressure cooker.
The great analogy. And under those extreme pressures, matter can behave in some pretty strange and wonderful ways.
Okay, give me an example. How does this extreme pressure affect the stuff deep inside planets and stars?
Yeah. Well, take the Earth's core, for instance. It's mostly made up of iron, which we typically think of as a solid. But under the immense pressure at the Earth's center, that iron actually exists in a liquid state.
Whoa, molten iron at the core of the Earth. That's wild. I guess it makes sense, though, if the pressure is high enough to melt metal.
Exactly. And it's not just about melting. Gravitational pressure can also force atoms closer together, creating incredibly dense states of matter that we don't normally see on the surface.
So it's like the rules of matter get rewritten under these extreme conditions.
In a way, yes. And those changes in the properties of matter have a profound impact on the structure and evolution of planets and stars. For example, it's the pressure at the sun's core that drives nuclear fusion, the process that powers the sun and creates all the light and heat we receive here on Earth.
So gravity is not only pulling things together, it's also creating the conditions for stars to shine.
That's amazing. And all this talk about pressure makes me think back to our conversation about launching satellites. It takes a lot of energy to overcome Earth's gravitational pull and get those things up into orbit.
For sure. Launching a satellite is a delicate balancing act between gravity, thrust, and trajectory.
Okay, walk me through it. What are the key steps involved?
Well, first, you need a powerful rocket to lift the satellite off the ground and propel it upwards against the force of gravity.
Right. It's all about breaking free from that initial grip of gravity, but then what?
As the rocket ascends, it gradually tilts its trajectory, aiming to achieve a specific horizontal velocity, what we call orbital velocity.
Ah, right. We talked about that earlier. It's about finding that sweet spot between going up and going sideways fast enough to stay in orbit.
Precisely. And that orbital velocity depends on the desired altitude of the satellite.
Yeah.
The higher the orbit, the slower the required orbital velocity. Right, because the farther away you are from Earth, the weaker the gravitational pull. So a satellite in a higher orbit doesn't need to travel as fast to stay up there. But how do we ensure that a satellite actually ends up in the right orbit? I imagine there's a lot of precision involved.
Absolutely. The timing and execution of the rocket's maneuvers are critical. At a precise moment during the launch, the rocket will release the satellite, giving it that final push to achieve orbital velocity. It's like a cosmic handoff, passing the baton from the rocket to gravity.
Seems like a carefully choreographed dance, with gravity as the ultimate partner.
A beautiful way to put it. And once a satellite is in orbit, it's not just coasting along effortlessly. There are still forces at play that can affect its trajectory over time.
Like what?
Well, even though space is a near vacuum, there's still a tiny bit of atmospheric drag, especially at lower altitudes. And then there's the gravitational pull of the moon and sun, which can tug on satellites and cause their orbits to drift.
So it's a constant battle against these subtle cosmic forces.
You could say that. To counteract these effects and keep a satellite in its desired orbit, we use onboard thrusters to make small adjustments to its velocity and orientation.
It's like a constant game of cosmic fine-tuning, nudging the satellite back on course.
Exactly. And the longer a satellite is in orbit, the more these adjustments become necessary. But it's a testament to our understanding of gravity and orbital mechanics that we can keep these machines operating for years, even decades.
It's truly remarkable. And, thinking about all the challenges involved in launching and maintaining satellites makes those missions to other planets seem even more incredible.
Oh, absolutely. Sending a spacecraft to another planet is a whole other level of complexity.
I can only imagine.
Yeah.
What are some of the additional challenges involved in interplanetary travel?
Well, for one, the distances are vast. It takes a lot more energy to escape Earth's gravity and send a spacecraft on a trajectory towards another planet. And then there's the challenge of navigating through the solar system, accounting for the gravitational pull of the sun, other planets, and even asteroids.
It's like a cosmic obstacle course.
You could say that. And then, once a spacecraft reaches its destination, there's the challenge of entering orbit around another planet, or landing safely on its surface.
Which requires even more precise calculations and maneuvers.
Exactly. It's a testament to the ingenuity of scientists and engineers that we've been able to accomplish such incredible feats of interplanetary exploration.
It is. And it makes you realize that our journey of understanding gravity is far from over.
I agree. There's still so much we don't know about this fundamental force, and those unanswered questions continue to drive scientific inquiry and inspire new missions of exploration.
Well said. It's been an incredible deep dive into the world of gravity, exploring its laws, mysteries, and its profound influence on everything from the falling of an apple to the dance of binary stars.
Yeah.
And who knows what amazing discoveries await us as we continue to unravel the secrets of this fundamental force that shapes our universe. Thanks for joining us on this cosmic adventure.